It's warm good evening to everyone. So the recording has started. So let me introduce myself again for the sake of those who will be watching it offline. So this problem solving session of structural analysis course will be held every Sunday from 6 to 8 p.m. I hope you would have received the information about the other problem solving sessions taken by the uh, um, other two scholars on, I think the other two people are on Mondays and Fridays. So I hope you would have received that information. So so this is one of those sessions. So I will be taking it from 6 p.m. to 8 p.m. on Sundays. So to introduce myself again, for the sake of those who have joined a bit late or those who will be watching it later, I'm Naresh Chockalingam. I'm a PhD candidate in the Department of Civil Engineering. I specialize in structural engineering. In particular, I study the mechanics of solids and structures subjected to large deformations. So today we'll be looking at some basic concepts in structural analysis. And so I'll start with a recap of what you may be already knowing after watching the lecture videos. And then we'll get into solving some problems that will help you to solve the assignments that are due by this Wednesday. I hope two assignments are due by this Wednesday. One is assignment 1, which is on the analysis of beams. So bending moments, shear force, finding reactions, and so on. And I think the second assignment is based on identifying equilibrium. So is the structure, sorry, not equilibrium, stability. Is the structure stable, unstable, statically determinate, indeterminate, and zero force members in trusses and so on. So let's quickly get started. Could anyone confirm that the blue screen, the PowerPoint, is visible? Anyone? Is it visible?
No.
Sorry? I couldn't hear anything. Is it? I'm sorry. Is it visible?
Yes, no, it's not.
Thank you. Thank you for letting me know. Yeah. So yes, let's quickly get into a recap of what we are going to what you should be knowing to solve these problems today. So the first thing is, you see, yeah. So the first thing that we'll be seeing today is what is a structure? So what is a structure? I hope you would have seen the introduction videos of Professor Amit Shah. So it is structure is basically a system of connected parts. Is that all? No. because we don't call many. So engine is not usually called a structure. So a system of connected parts that is used to support a load. So for example, what you must be knowing, so you must be familiar with a lot of structures. You call this a portal frame, you call this a truss. All these are structures. So what differentiate? So it should be supported, should be adequately supported so that it can transmit certain loads. Fine. So what makes it different from a mechanism? So it is not a mechanism. So what is a mechanism? Mechanism does not support a load. It will accelerate. So if you have an assembly of members and when you subject it to a certain set of loads, it shouldn't accelerate. None of its components should accelerate. It should deform. So it should deform and transmit loads. So transmit loadings to support. So all of you would be very much familiar. So you have some solid, you support it somehow, apply certain loads, it wouldn't deform in such a way it wouldn't accelerate, and if it deforms, it is called a structure. That's all, very simple. The next thing is what is analysis. So you have a structure, right? You have something called structure. You give it some input, right? You give it some input, it will give some output. For example, if you take a beam, right? So you must be familiar with beams. This is a simply supported beam. This is a structure because it doesn't accelerate under normal loading. It is a structure. What is the input you give? You can give a UDL. You can supply uniformly distributed load, or you can give a point load, or whatever. That is up to you. So this is a structure. You're giving some input which is low. And what does it do? It deforms. Correct? So how do you measure the deformation? You can call something called deflection, which is some W of X. So you give some load which is Q of X, and you get some response which is W of X. Or you can also call the response as the bending moment. You can have a bending moment. You can take the maximum bending moment as the response. You can take the shear force as the response. So anything can be a response. So given, something else. So given a structure subjected to some loads, which is your input, the structure responds in some way. And studying that response, right? Studying or finding that response. Finding the response. That is called structural analysis. Simple. That's it. So you must be very familiar with these idealizations. Yes. Yeah, I think some of your mics are accidentally unmuted. So I guess you may have to mute. I'm muting them. So what is idealization? Why? Because in reality, so what I just drew here, right? What you call this, a hinge joint. You have this fixed joint. It's a fixed joint. This is a hinge joint. So in reality, you don't have joints like this. You have something. Suppose you have a steel collar. Sorry, this inclined a bit. A steel collar, and then you have a plate, and then you have a beam connecting this. You can weld it here. So in reality, these are not rigid members, right? These members are the joints, they're not rigid. Or they're not infinitely flexible. So basically, this will deform a bit, but it will transmit some moment. So in reality, there are no perfectly fixed joints like this or perfectly hinged joints like this. So the reality is somewhere in between. But you idealize them as this. So idealization is some kind of an approximation, which is very close to reality. It simplifies mathematics. That's it. Simplify the analysis. So this is a kind of joint idealization. What else are you aware of? So you may also be aware of the load idealization, right? So if you take a beam and you apply a midpoint, take a simply supported beam, you apply a midpoint. In reality, no load can act in a at a point like this. So in reality, we'll have, say, if it's a steel beam or a concrete beam, have a concrete beam which is supported by some way. We have some reinforcements and supported some way. And whatever load that comes on it, suppose a person is standing, it will always be distributed in a small space. If you take an area here, we'll have distributed loads. We'll have a distribution of forces. But when the area of distribution is very small, so this area of distribution is very small compared to the size of the structure, you idealize it as a ohmic load. So this is something basic. And what is superposition? Again, for linear, elastic analysis. This is very important. Only for linear elastic analysis, there is something called the principle of superposition. So we'll be using all these principles while we solve problems. That is the only reason I'm going through this. So in layman's terms, a structure is subjected to two inputs. Right? So it could be two load inputs or two displacement inputs, whatever it is. So if you have a structure, say a cantilever beam, simultaneously subjected to, say, a point load here and a uniformly distributed load here. So what happens is, if you're doing a linear elastic analysis, so what is linear elastic analysis? Displacements and rotations are very small compared to the size of the structure, some characteristic size of the structure. And the material is linear elastic. Under these conditions, you can always suppose you're interested in the tip deflection, delta. So if you call it this delta, you can always decompose it into two scenarios. One, when the UDL alone is acting, so if it deforms by delta 1, and the other scenario, when only the point load is acting, let's call it delta 2. So you can always decompose the total displacement as delta 1 plus delta 2. So when a structure is subjected to, when a linear elastic structure is subjected to a combination of different loads, the total response is a superposition of each of the loads acting individually. Okay. So I hope this should be clear because this is quite basic. We get to the next part. So the other important concept that we'll be using for our problem solving is the idea of equilibrium. So what is equilibrium? So equilibrium, what you may be aware from physics, is kind of static equilibrium. We're interested in static equilibrium. So basically no acceleration. So that is what defines our structure. So there shouldn't be any acceleration. And what this means is forces and moments are balanced. So there are three conditions that define the equilibrium of a planar structure. In total, there are 6. So one is the sum of all forces along the x direction should be equal to 0. Sum of all forces along the y direction should be equal to 0. Sum of all forces along the z direction should be 0. Not only that, sum of all moments about the x-axis should be 0. Sum of all moments about the y-axis should be 0. Sum of all moments about the z-axis should be 0. So these in a vectorial form, you can always simplify this as sigma f vector is equal to 0 for all, and the summation of vectorial moments is equal to 0. So if the structure is coplanar, right, that is, the structure entirely lies in a plane, all the loads acting on the structure act in a plane, and all the boundary conditions, fixed, all of them act in plane. In that case, you can always simplify this to a set of 3 equilibrium equations. So how does that happen? You just knock out this sigma fx equal fz equal to 0 because the z direction doesn't exist. Rotation about x involves movement in the z direction. So you can strike off this and this. So basically, you will have just 3 equilibrium equations, which are sigma fx is equal to 0, sigma fy is equal to 0, and sigma mz about to equal to 0. So these 3 equilibrium equations are both necessary and sufficient for the equilibrium of a planar structure. The next issue is stability. So when do we call a structure to be stable? So the general idea is you take a structure which can be in equilibrium. Suppose you take this portal frame, let it be in equilibrium. You perturb it slightly. What happens? It deforms in a certain fashion. It deforms in a certain fashion. So when you perturb the structure slightly, it shouldn't accelerate. So it could very well be in equilibrium, but under perturbations should not accelerate. It shouldn't become a mechanism. So when does this happen? Basically, this happens sometimes when if the structure is inadequately supported. That is, suppose you've considered this, right? If you take this beam, which doesn't have a support this side, if you apply a vertical load, it will accelerate, it will just rotate. So this is inadequately supported or partially supported. For example, this case. In this case, the structure can very well be in equilibrium, but if you slightly perturb, if you apply a small horizontal force, it is going to accelerate in this direction. So this is not stable. The reason here is the reaction forces are parallel. So this happens when reaction forces are parallel or concurrent. So if you have a structure, could be anything. If you find that all the reaction forces on that structure are parallel, in this case, then it will obviously accelerate in the direction orthogonal to this direction. So if you have parallel reaction forces, it is going to be unstable. Or if you have concurrent reaction force, you take the structure. So this, it seems that it can easily satisfy it. It will remain stable under any applied force. But if you apply a moment about the point of intersection, it will freely rotate. So if you have a concurrent reaction forces or parallel reaction forces, the structure is unstable. So this can be used as a check to identify stable or unstable reaction, stable and unstable structures. The other issue that we are interested in is determinacy. So let me add another page. So as I said, typically, if we have a structure, right, we can determine the reactions and the member forces using the equilibrium equations. Okay. Usually we determine the reactions and the member forces using the equilibrium equations. But in some cases, equilibrium equations may not be enough. So for example, here you have how many reactions? You have 1, 2, 3 reactions. 3 unknown reactions. And how many equilibrium equations you have for a planar structure? You have 3 equilibrium equations. So using this, you will get a system of 3 by 3. So you'll get 3 unknowns. So you'll have you'll get a system of 3 by 3 equations. And this is solvable. So so when you have exactly equal number of unknowns and the number of equations to solve them, it is called statically determinate structure. So what does statically mean? It means that the equations of static equilibrium are alone sufficient. So today, all the structures that we look at will be statically determinate. All the structures that we'll be analyzing will be statically determinate structures. Statically indeterminate structures will come at a later point of this course. So if you have statically indeterminate structures, for example, you consider this P, it is fixed at both the ends. So you know if it is fixed, what does it do? The beam at the support, it resists a vertical force, a horizontal force, and a moment. Similarly, this side, it resists a horizontal force, a vertical force, and a moment. And in general, all these 6 reactions, so there are 6 unknown reactions. But you have only 3 equilibrium equations. So in this case, you will get a flat system. You will get a 3 by 6 matrix, 6 cross 1 is equal to 3 cross 1. So you get you have only 3 equations, but you have to solve for 6 unknowns. So in general, this is not solvable. So this is statically indeterminate. You need more equations. So you need more equations. Let me need more equations. So where does that come from? If you remember your strength of materials, it comes from compatibility. So this aspect of structural analysis we'll do it later. So today we'll be limiting ourselves to statically determinate structures and to determine if a structure is statically determinate or indeterminate. Good. So let's get to the next aspect. Yeah. So what is the procedure to find the reactions, right? So what is the recipe to find the reaction? So the first step to find the reactions is always isolate the structure. Isolate and draw a free body diagram. So this is one of the most basic steps. If you have a yeah. So again, so you may be having some beam. So this is a cantilever beam. So the first step is to isolate. So remove the support. So first remove the support. You can add some forces here.
Sir, I am unable to view the screen.
Oh, is it? Let me. Am I audible now?
Yes, sir, you are audible, but your screen is not visible.
Is it not clear?
No, sir, your screen is not, I am not able to see the screen. It's very blank.
I'm sorry. Can you repeat it? Is it clear now? Is it audible right now?
It is audible, sir, but the screen is blank. So I am not able to view the screen.
Oh, are the others facing the same issue? Is the screen blank or?
Visible, sir.
Sir, it's
Okay,
not
so-
visible on mobile, it's visible on laptop only.
Oh. Hmm.
Visible in mobile also, sir.
Oh, okay. Maybe you have to. Anyway, I'm recording it in case you're facing any network issues or in case you're facing some technical issues. I will share the video on YouTube on the YouTube page. You can watch it later. But how many are facing this issue with mobiles? It's not visible on mobiles. Okay, only one. I would suggest you just click on the name. I think you can see my name, right? NS. So you just tap on it. Sometimes that will resolve the issue. Is it resolved?
No, sir, no, sir. Shall I reconnect it, sir?
Sorry?
Shall I cut my call and reconnect it again?
Yeah, you can join in the same link. It will be working. Yeah, I'll proceed with the class. You can look at the missed portions later on. So yes, so as I said, the first step in, sorry, I didn't select it. So as I said, the first step in solving for the reactions is, so first denote the reactions, remove the support and denote the reactions by certain forces. You can use any sign convention, but you should be using a consistent convention. So in this case, suppose this beam is AB. You call this the force, vertical force as AY, the horizontal force as AX, and the moment as MY, MA, right? So first isolate it, and when you show all the forces on this is called a free body diagram. The body is free, and you're depicting all the forces acting on it. And then the second step is to yeah, so isolate the structure, determine, so denote this. Then the second step is to enforce the equilibrium equations. So for this body, you just write the equilibrium equation. Suppose the applied load is Px, Py. So what does sigma Fx equal to 0 imply? It means Ax minus Px, right? If right, you use the convention. For example, right acting forces are positive. Upwards is positive. Counterclockwise moments are positive. So Ax minus Px equal to 0. Similarly, sigma Fy equal to 0 means Ay minus Py equal to 0. And what are the moments? Moments about the point A. So moments about the point A means what is the moment acting there? MA. So these two forces, AX and AY, will not contribute to moment because they're acting through the point. The lever arm is 0. Instead, PY will contribute. So how does it? It is clockwise. Sorry, MA. Yeah, moment about this point. So clockwise moments are negative, minus ME minus PY into L equal to 0. So PX is also acting through the same point. That has 0 lever arm. So for this example structure, this is how you solve it. So you have 3 equations and 3 unknowns. This is one unknown, this is the other unknown, this is the other. You can solve for this. So how do you get the internal forces? So what are internal forces? So as I said, if you have a structure, right? Have some structure, you subject it to some loads, and it is supported somehow. So how is the structure transmitting these loads to this support, right? These loads have to be transmitted to the support. So how does that happen? It happens by deformation. So as the structure deforms, right? As it deforms, the material here gets stretched or sheared, or there are various ways in this. A single point of material stretching because there are atoms, right? So when you subject them to some loads, the bonds will stretch, they will elongate or they will contract, their angles can change, and all this can happen. So because of this, there will be internal forces that are generated. So as the structure deforms, material will resist, and there will be internal forces. So we design all structural components for resisting these internal forces. For that, it is essential to know what the internal forces are. You know that internal forces are equal and opposite. From Newton's third law, you know internal forces are equal and opposite for a structure that is in equilibrium. So if you consider the structure as a whole, you cannot determine the internal forces. So you know that, suppose this is a beam. If you take a point here in the beam, there will be internal forces. Otherwise, the beam will not deform. As the beam deforms under some loads, there will be internal forces that are generated such that this force is transmitted to the supports. So how do you determine the internal forces? As such, if you apply the equations of equilibrium to the entire structure, you cannot get it. So the trick is to expose the internal forces. Sorry. Yeah. So to do that, you have to cut the. So if this is a beam, just cut it here, right? You make an imaginary section through the beam. So you'll get 2 parts. Suppose it is simply supported with some loading. You get 2 parts here. And depending upon the type of the structural member, you will have internal forces. For example, in this case, you'll have an internal axial force, shear force, and bending moment. Similarly, this side you'll have an axial force, shear force, and bending moment. And note that they are exactly equal and opposite. Now apply the equations of equilibrium to this part separate. So again, coming to this, the recipe is as follows. So the first step in determining so step 1 for determining internal forces is again always isolate. You have this subjected to some isolate it. Yes. Denote the unknown reactions. M Fx Fy P and get the free body diagram. Step 2 is find the reactions. So for statically determinate structures, you can find the reactions by equilibrium alone. So I just showed how to do it. You can use that. The third step is, so if you want to get the internal forces at this point, say at this section, make an imaginary cut at this point and draw either of the two parts. Either this or this. Here, denote the unknowns as n of x, v of x, m of x. On this part, it is essential that they're exactly equal and opposite. N of x is upward, v of x, and it should be clockwise, m of x. Now take any of the two, either this or this. So once you have determined the reactions, everything else is known in this, right? So once you have determined the reaction, except for these three unknowns, everything else is known. So enforce three equations of equilibrium. To either of those. So finally, if you have a consistent sign convention, if you get negative values, it means assumed direction is up. So it just means reverse the convention. That's all. So this solves the problem for internal forces perfectly. So yeah. So let me pause here for if there are any questions, and then I'll quickly get into some preparatory problems. Then we'll have a set of 10 questions from last year's assignments, which will help you solve this year's assignments. So let me pause here. If there are any questions, I can take. No questions. Okay, then let me go ahead. Yes. So based on the discussion we just had, could anyone try out this? What do you think this problem is? So you're given a structure and this is a rigid joint, transmits a moment, and this is a pin joint. So this transmits no moments. This is hinged, so it has two reactions. And this is also hinged. So can anyone give a try? Do you think it is statically determinate, indeterminate, stable, unstable? What is it? Okay, let's go systematically. So for stability, so first question is stable. Is it stable? So to determine that, perturb structure. So if you apply a small load, right? What does the deformed shape look like? What you can predict is, because this is free to rotate. This is not free to rotate. This comes like this. Again, this is free to rotate. So this is how it deforms under a horizontal load and also on the vertical load. So basically, this doesn't accelerate since it is fixed sufficiently at the support. So it is stable. And again, coming to determinacy. What did I say? So if you should check if the number of equations is equal to number of unknowns. Is this satisfied? So what are the unknowns in this problem? So we have how many equations we have? So globally we have 3 equilibrium equations. And how many unknowns we have? We have 4 unknown reactions. But is it indeterminate? No. The reason is, as I said, if you try to determine the internal forces, right? So you can make a cut here, you can make a cut here, you can make a cut here. So this member has 3 internal forces. This section also has 3 internal forces. What are they? They're axial, shear, moment. Similarly, here you have axial, shear, moment. Again, same thing. So if we take it as A, B, C, D. So for the member AC, for the member CD, and for the member BD. Same thing. So totally you have 3 plus 3 plus 3 plus 4. So 9 plus 4, you have 13 unknowns. And how many equations you have? But each of these members, right? The member AC, CD, and BD have to be in equilibrium individually. So you have 3 into 3 again 9 plus 3 equations. In addition, you have this as a hinged one. So what you know is the moments, if you take this or this, the moment acting at D and B. So this moment is 0. So MD is equal to 0 in both these. So you have one additional equation coming from the hinge condition. So again, this has 13 equations. So since this is satisfied, this is stable and determinate. Clear? Is there any doubt? I'll clarify right now. Hello? Okay, I guess there are no more doubts. Okay. Now getting to this problem. So all members are connected by pins. So you see this is a pin joint, 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 this is a pin, this is pinned. So this panel alone, as such, it looks like it is stable. But here, if you see, this is pinned and this is also pinned. So if you apply a horizontal force here, what happens is this panel simply rotates. Because it is free to rotate, right? It is free to rotate. Each of these joints are free to rotate, and this can simply slide. So this not only rotates, but it can also slide. And there's nothing resisting this deformation, so it forms a mechanism. So you slightly perturb it. If you feel so under a perturbation, if there is nothing that resists its motion, it does not deform and it moves rigidly. So it becomes unstable. So if a structure is unstable, it doesn't matter if it is statically determinate or indeterminate. So basically, it is a mechanism. Mechanism is the correct answer. Why? As I said in the first introductory session, a structure should not accelerate. If it accelerates, it is a mechanism. So under a small perturbation like this, if you apply a certain load, the support should be adequate that it resists the applied load and it generates some reaction so that the structure deforms. It shouldn't accelerate. So in this case, it accelerates and it forms a mechanism. So it is neither statically determinate nor indeterminate. It doesn't matter. It is a mechanism. So again, this is simple. So what is a statically indeterminate structure? As I said, the equations of equilibrium are not sufficient. So equations of static equilibrium are not sufficient. You need additional conditions called the compatibility conditions. So a statically indeterminate structure, by definition, is one structure which cannot be analyzed only by the equations of static equilibrium and also requires what are called compatibility equations. So that is a simple thing. We'll go to the next question. Yeah, so this is an interesting question. So what are the number of zero force members? So when does zero force happen? So you take this truss. So consider this joint, right? So if you consider this joint, so what are the assumptions in a truss? One, all members are actually loaded. And the other thing is loads are always applied at the joints. So does this satisfy? Yes, the loads are always applied at the joints, but yeah, and they're all axially loaded. So if joints do not resist any movement. So if all joints have been pin connected, in this case, this one, if they're all pin connected, they are free to rotate and they do not generate any movement. So in this case, it's a truss. And if you consider the equilibrium of a joint, so if this truss is under static equilibrium, each part of the truss has to be under static equilibrium. So if you consider this joint, the only forces that are acting are this one and this one. So if you enforce the equations of equilibrium, what do you get? So what are the vertical forces? So if you call this F1 and call this F2. We can resolve this vertical force in the two directions as F1y and F1x. So in this case, what do you get? You get F1y plus F2 doesn't have a vertical component equal to 0, which means F1y is equal to 0. But what is F1y? F1y is the force F1 sine this angle, the angle between this theta, equal to 0. So this theta, what is it? It is 3/4. So sine theta is tan inverse of 3/4. So this comes to something like 37 degrees or so. Sine of this is 3/5, right? 3 by square root of 3 square plus 4 square. So sine theta is not equal to 0, which means F1 is equal to 0. So this is a zero force member. Since F1 equal to 0, if you enforce the other equilibrium equation, sigma Fx equal to 0 at this joint, what do you get? F2 plus F1x equal to 0. But what is F1x? It is F1 cos theta equal to 0. So cos theta is again not equal to 0, which means and F1 is 0. So F2 is also 0. So this is also a zero force member. Now coming to this point. So one thumb rule that you can know is, so if two non-collinear members at a free joint are always zero force. So this is rule number 1. If you anywhere you find two non-collinear members at a joint, if you cannot do the same thing for a collinear assembly. So if you have two members which are along a straight line, you cannot call it a zero force member. But if you have two members that are not at 180 degrees, that are not at 0 degrees or 180 degrees, say like this or something like this, obtuse. In all these cases, this joint, if it is not loaded, if it is a free joint which is not loaded, or it is not supported, it shouldn't be supported, it shouldn't be loaded, and the truss members are not collinear. Under these conditions, both these members will be a zero force member. That is one. And there's the other rule, right? So the second rule is, if you have a third member in connection with two collinear members and the joint is not loaded like this, right? You have one member which is connected to two members that are not loaded. Two members that are collinear and the joint is not loaded. So this should not have any reaction and this should not have any load. If you have a third member like this, then that is a zero force member for sure. So this is a zero force member. You should be cautious that these two need not necessarily be zero force members. So either you should have two members that are not collinear and the joint is not loaded, or you have three members, two of them are collinear and the joint is not loaded or supported. In this case, the third member alone, which is not collinear, will definitely be a zero force member. Why? Again, you consider the equilibrium of this. So consider this as member 1, member 2, member 3. Assuming all are tensile, you will have F1, F2, and F3. You just enforce the equations of equilibrium in the y direction, sigma Fy equal to 0. You get F3 sine theta equal to 0 minus F3 sine theta equal to 0. But again, as I said, if they are not collinear, theta, if it is not 0 or 180 degrees, it will be out of this line. So in that case, sine theta is not equal to 0, which means F3 is equal to 0. So this is the second rule. If you have three members that are not, if you have three members with two of them collinear and the other one is not collinear, and the joint should neither be supported nor it should be loaded. Under these conditions, the non-collinear member will be a zero force member. So using these two rules, you can identify how many of these are zero force members. So as I said, this one and this one are already zero force members because this joint is not loaded and they are not collinear. So coming to this joint. So this one, you have two collinear members, which is this, and this is not collinear, and this one is not collinear with them, and this joint is free. It is not supported nor it is loaded. So this is a zero force member. Applying the same logic here, it's identical. So this is a zero force member. So how many zero force members you have for? So you have 1, 2, 3, 4. But is that all? No. The reason is this. So consider this joint. So this is a zero force member, which means there is no force in this. You have a vertical member and a horizontal member here. So here is the third rule. So if there is a joint at right angles and the force is acting along one of them, the other one will be a zero force. Again, reason is apply equilibrium equations here. So sigma, so apply P, Fy equal to 0. So at this joint, you have force F2, F1. So, or sorry, Fx equal to 0. What does it mean? The only force acting on x direction is F1. So F1 equal to 0. So by that logic, so this member is a zero force member. So it doesn't transmit any forces onto this joint. So this structure is the same as this structure. You can remove the last panel as such. Because these two members are not taking up any force, they're useless. So you can remove them. And by this logic, this is also a zero force member. So totally you have identified 1, 2, 3, 4, and 5. So there are totally 5 zero force members in this structure. Yes. Again, let me pause here because we are getting into more involved, mathematically involved questions. Are there any doubts so far? Any doubts? Could anyone unmute and say if everything is okay?
No, sir.
No doubts?
No doubt, sir.
Thank you. Thank you. Okay, let's get into these more involved questions. They're more interesting. Okay, so this is about computing. So this is about computing the computing the line loading on a beam. So in reality, beams are like this. As you see, there is a wall that is supported on a slab. So this is a slab. And below this, you have the I-beam, which is supporting all the load. So in real constructions are like this. But as I said, we normally do idealizations. So this one is too complicated to analyze. This is 3D structure. This is too complicated to analyze. So we idealize this as a simpler structure. How do we do it? We take this. So consider this. So this, let me draw this cross-sectional view of this. We have a brick wall. And you have this slab. It's a concrete slab. And this is supported on the steel beam. So the first idealization is, so there is some load that is coming out of the beam. If you take the beam as such, it will bend. It will bend like this. It will bend to some shape. So how now our goal is to analyze the beam. Analyze the beam. And as I said, what is analyze? Given some inputs, we want to find a response. So what are the inputs? So find the inputs. So one idealization is beam theory. So all of you would be familiar with this. From this 3D structure, you're going to the beam theory, which is a 1D theory. We are treating this beam as a line. So we'll take this beam as a line. And they said, yeah, so it is a line. It is treated as a line with some support conditions. We don't know. It could be some support conditions. It is just representative, but in reality, it would be some support conditions. What is the other thing that we are idealizing? So this load, we are treating it as, so since it is uniformly applied, right? It is of the same length on both sides, 1.5 meters, 1.5 meters. And this is uniformly applied. So you can replace this system with a statically equivalent set of forces. So instead of considering this distribution of forces in the cross section, we'll take the resultant. So we integrate out all the forces acting here. So if we take this beam, there are so many forces acting here. We'll apply the resultant to this beam so that the loading is a function only of x. So this is the second idealization we are doing. So next, it is very simple. What we are looking at is very simple. So in this case, so much weight of, what is the load that comes onto the beam? It is this entire weight of concrete plus weight of brick. So what is the weight of concrete? It's very simple. Suppose the density of concrete is rho c into this density. What is the volume? So if you consider 1 meter, right? You want to find out the load that is coming onto the beam per meter. That is what they have asked. So determine the loading on the beam per unit length due to the weight of the slab. In this case, rho c into distance is 1 meters. So volume is length into breadth into height. Length is 1 meters. So breadth of concrete is 3 meters into, or let me put this through. So it is 1. So breadth of concrete is B concrete. Height of concrete is H concrete. So this will give the mass, weight will be into G plus rho brick into width, length is again 1 because we want to find per unit length into height of brick into G. So this is what we need to find out. So it is given rho C is what is rho C? 2400 kg per meter cube. Rho B, you can take it as 1800 kg per meter cube. Height of concrete is 0.12 meters. Breadth of concrete is 3 meters. Height of brick is 3 meters. Width of brick is 0.35 meters. What else? And G you can take it as 9.81 meters per second square. So if you just substitute all these values, you can get what it is. So if you want, I can give you the answer. Has anyone tried out? Would you try this out? Right? Anyway, you can try it out later. The answer would be around 33. Sorry. That's all it. You should get the answer roughly around 31 kilonewtons per meter. 31 kilonewtons per meter. So this is a very simple problem. You're given all the dimensions, you're given the densities, and you're given all the other specifications. So it is just a matter of finding the volume multiplied by the density multiplied by G so that you will get the force per unit length. So force per unit, force per meter run you will get. And that force will be in newtons since you have used SI units, kg, meters, and meters per second square. The force you get will be in SI units. You just have to convert it to kilonewtons divided by 1000. Let's go to the next question. So this is a B. So this one is, now this is a given structure. So let us idealize it. So as I said, first step is idealizing. So we need to find the support reactions. So this is a fixed support. You have a internal hinge, right? So as I said, internal hinge means at that point, the connected members are free to rotate. The angle between the connected members can change freely. You have an intermediate support at B. And you have another internal hinge at E. And finally, you have an end support. So this is the beam we are looking at. So this is A. This is B. This is B. This is E. And this is C. So at the middle, you have a force of 30 kilonewtons. So yes, come on. Now, what is step 1? Yes, what is step 1? Does anyone remember? To find the support reactions? I just said in the introduction session, what is step 1? To find the support reactions? Okay, fine, let me go ahead. So step 1 is yeah. So step 1 is isolate and draw the free body diagram. So is this a statically determinate structure? Yes. So isolate each component. So consider the span AD. What are the forces that act here? You will have AX, AY, and an unknown moment at MA. At this point, it is internal hinge. So you can say that there is no moment MD. You cannot have a moment at this point. It is free to rotate, so it doesn't generate a moment, but it will have a vertical reaction dy and dx. Now consider the next part. dB. So there is a mid-span loading of 30 kilonewtons. At D, you should draw equal and opposite forces. So this is opposite to this dx, this is dy. Since there is no external loading at this point, the joint has to be in equilibrium, and joint is a point. So the forces that come onto this joint should be equal and opposite. Similarly, B, you can have dx, dy, and this moment MB. So since this support is an intermediate support, this will, okay, no problem. So just consider this as B1Y because you will have another part that is coming from the other. So here, because of the force that is acting on this joint. So if you take this, you will have this joint alone, you'll have B1Y acting from this span of the beam. So this will act opposite to it. And from the right part, you will have some B2Y. This is B1Y. And on the right part, that is BE. You will have BY2. So you'll have BY2 also acting on the same point. BY2. Not only that, there will also be this moment MB. So since the beam is continuous, if you take a small section of the beam, very small section, infinitesimally small section of the beam above this support, right? Since the beam is continuous, the moment that acts on both sides of the joint will be equal. But the shear force, that is this side, you will have a shear force of By1, and this side will have a shear force of By2. Those need not be continuous because you have some additional concentrated force that is coming from this support. Could be some RB. So these two will differ by RB. That is the reason we have taken two different notations. Then coming to the last span. So again, this is an internal hinge. So this cannot have any moment. So it'll have an EX and EY. Again, here you should draw the opposite direction, EY and EX. And this is connected to C. And C is a roller, so it can have only CY. So that is clear. We got 1, 2, 3, 4. And yeah, 4 spans. We have isolated all this and we have drawn the free body diagram. Now coming to let us quickly enforce equilibrium equations. So what is step 2? Equilibrium equations. So take this span, right? Take this span. So immediately you can see all horizontal forces are 0. So AX equal to DX equal to BX equal to EX equal to 0. Why? Consider this. So this is EX. If you enforce sigma fx equal to 0 for this, there is no other force acting here, which means EX is the only force, that is 0. Now come to this point. So the EX is acting here, this is EX, and here you have a BX2. So EX is equal to BX2 is what you will get. Since this is 0, this is also 0. So slowly it propagates. So this BX is 0, which means DX is 0. And if the DX is 0, and if DX is 0, we get AX also equal to 0. So all horizontal forces are 0. So wherever you see a structure like beam along the line and it has only vertical forces, then all horizontal reactions and all the horizontal reactions and the horizontal internal forces, they are all 0. Now coming to step 2. Equilibrium equations. That's all. So consider the last one. So set sigma m, this is the last. You have EX, you don't have EX, it is 0. EY acting here and CY acting here. Just set sigma ME equal to 0, which means take moments about this point. What is the length of this? It is 6 meters. So you'll get CY into 6 equal to 0, which means CY equal to 0. But not only that, EY minus EY plus CY equal to 0. Where does this come from? Sigma FY equal to 0. Since CY is already 0, you also get EY equal to 0. Now what is asked here? They're asking the vertical reaction at C. So CY is equal to 0 is one thing. Then we have to find A. Now EY is 0. Now consider the next span, right? The span, this one, BE. So if you consider BE, there is no force, there is no horizontal force, or there is no vertical force coming at point B. So at this point, you have the beam like this. You have MB, you have BY, so BY2, BY2, and EY is 0. So what do you get? It means BY, if you again enforce sigma Fy equal to 0, because EX is 0, EY is 0, and also it cannot transmit any moment, it's a hinge. It means if you enforce Fy equal to 0, you get BY2 equal to 0. And of course, MB is also equal to 0. Now let us come to the span dB, right? That is the most important span, dB. So here, if you draw the free body diagram of dB, MB is 0. We already got this. MB is 0. And then the force By2 is 0, but we don't know what By1 because left side and right side, the forces are not equal because of the support reaction. So what this acts as is, because moment is 0, it acts as a hinge. And this side you have an internal hinge, and here you have a support. So here you have dy, and here you have by1. This is 30 kilonewtons. So this is nothing but a simply supported beam. So as usual, you can take moments about the point D. If you take moments about the point D equal to 0, you'll get by1 into what is the span? It is 4 meters minus 30 into this lever arm is 2 is equal to 0, which means by1 is equal to 15 kilonewtons. Now enforce sigma Fy equal to 0, you get by1 plus dy, sorry, minus dy, it's in the other direction. minus 30 kilonewtons is equal to 0, which means dy is equal to dy is 15, right? Dy is 15 kilonewtons. So you'll get dy minus dy 15. So dy you'll get as minus 15 kilonewtons. So as I said, if it is minus, just reverse this thing. So you just, it means this is minus 50, this is minus 50. Now come to the last line, which is AD. So if you just consider this portion, you get what you have as a cantilever beam. And dy we found it as minus 50. On this plan, dy is upwards, which means it is minus 15. So it is 15 kilonewtons downwards. So what is the fixed end moment here? The lever arm is 6 meters. So you get the moment as minus 6 into 15 kilonewtons, since it is clockwise and hogging. So basically, the answer to this problem is 6 into 50. So the moment at A is 90 kilonewtons clockwise, and at 90 kilonewton meters clockwise. And the reaction at C is 0. Any doubts? Any doubts? Shall I go ahead? Is everything okay until now? Okay, I assume everything is okay. Let us go ahead. Okay, let's go to question 3. So this is a frame. This is a frame structure. Let me add another slide so that it's easy to. So what we have is a frame structure. Again, as usual, it is considered step 1. Step 1, isolate A, AB subjected to this loading. And this is a hinge, so we'll have AY and AX. Is this a hinge? No, it is not a hinge. It is built in. So it is continuous with the member BC. So you can have dx, dy, and a moment MB. Now let us look at the member BC. So you should have an equal and opposite moment MB, equal and opposite force Bx, equal and opposite force B. There are no external forces acting at this, external forces of moments acting at this. Just a minute. Yeah. There's no external force or moment acting at this junction, so it is continuous. Whatever moment you have here, it should be the same moment this side. Because if you consider the junction, we'll have MB, dx, and dy. So you cannot have any additional, you cannot have any discontinuity in the moment functions. So you'll have equal and opposite forces. And the point C is an internal hinge, so it cannot resist any moment. So MC equal to 0. What you have is a Cx and Cy. Now let us look at the member CD. CD. So you should have an equal and opposite Cx and Cy. And D is also pinned, so you'll have only dy and dx. Clear. Now what is asked is find the horizontal and vertical reactions at the point D. So let us go about it. So this structure is statically determinate. You can check how many unknowns we have. So what are the unknowns? You have AX, AY, BX, BY, MB, CX, CY, DX, DY. You have 4 plus 3 plus 2. So you have 9 unknowns. And how many equations? You have 3 equations of equilibrium for each of the part. Here you have 3 equations. Here you have 3 equations. Here you have 3. So 3 into 3 you have 9 equations. So since they are equal, it is statically determinate. So let us solve the problem. Consider the member CD, and you take moments about the point C. So if you take moments about the point C, sum of all moments in the z direction about the point C equal to 0. If you enforce this, what do you get? dy acts through the same line, so the lever arm of dy is 0. Cy and Cx act through the same point, so they also have a lever arm 0, so they will not contribute to moment. So only component that contributes is dx. So it creates a counterclockwise moment about C. So what you get is dx into 6 equal to 0, which means dx equal to 0. So we have already solved one part of it. If dx is 0, what does it mean? Cx is also equal to 0. Now enforce sigma Fy is equal to 0 for CD. In this case, what do you get? Cy minus Cy plus dy is equal to 0, which means Cy is equal to dy. Now this is done. Now consider this this structure, right? Structure A, B, C. So this is subjected to some loading here and 2 other loads middle of this panel. Now take moments about the point so that now we don't need to solve for by and dx. If you just reassemble them, we are not interested in those. We only want the vertical reactions at the point D. And we already found that dx is 0 and Cy is equal to dy. So to find dy, it is enough if you find Cy. So what do you have here? You have Cy. And what is Cx? If you enforce Fx equal to 0, you get Cx equal to 0. So the only unknown reaction in this case is Cy, Ax, and Ay. This is 25. This is 20 kilonewtons. And this distributed load of 7.5 kilonewtons per meter. Now let us take moments about the point A so that we get Cy directly. If you take moments about the point A, you can eliminate Ax and Ay. So what do you get? You get minus 7.5. This is the load per meter run. What is the total force? It acts through a length of 4 meters. At which point, since it is uniformly distributed, the resultant of the force acts through the centroid of the load. So into 2. This you can easily verify if you integrate a uniformly distributed load. Suppose you have uniformly distributed Q of x over a length L. The resultant acts at the point integral Q of x dx from 0 to L divided by. Yeah, so the resultant acts at the centroid, basically at the centroid by dx. So this is where the resultant will act. Integral dx 0. So 7.5 into 2. This is a counterclockwise movement. So minus. Sorry. Minus 7.5 times 4 into 2. Minus 1.5 into 25. So this 25 acts at a distance 1.5 and this 20 acts at a distance 3.5. And that also creates a counterclockwise movement. Minus 20 into 3.5. But the Cy is acting upwards. Cy is acting upwards at a distance of 2.5. 2 plus 1.5, which is 3.5 plus 1.5. So plus 5 into Cy equal to 0. So that's what you can just solve for this. You have so this is one equation with one unknown. You solve for Cy, you get Cy is 33.5 kilonewtons. And since Cy is equal to dy, you get the reaction at D is dx is 0 and dy is 33.5 kilonewtons upwards. So this is the answer. Any doubts? Any doubts? Okay, I hope there are no more doubts. We'll go to the next one. So this is the simpler problem. We have. Again, let us idealize the structure. So step 1, idealize it. Step 2, just isolate it. So you consider the span AB, right? It is just a single span. You have A, B. At A, you have a fixed support, so it resists the vertical force AY and the moment MA. And here it has the linearly varying load W with the maximum intensity W, and it varies from 0 at the point x equal to L to W at the point x equal to 2L by 3. So this is the point x equal to 2L by 3. This is L by 3. So consider this structure. Now it is simple. We just have to determine the bending moment at section A. So bending moment at section A is same as the reaction at the section A at the point A, which is MA. So you just have 3 unknowns and 3 equations. So you have 3 unknowns, which is, yeah, we have already used one equation, that is sigma fx equal to 0. Since there are no horizontal forces, implies no horizontal reactions. And this is only for B. You cannot use it for a frame, because in a frame, horizontal reactions can be developed even if there are no horizontal forces. So be very cautious. So for example, if you have a structure like this, this will definitely generate a horizontal force, but only if you have a beam, if you have a single beam which is horizontal, which is along a straight line, and on that line, if you have only vertical forces and no horizontal forces, then there will not be any horizontal reactions. So if we want to find out bending moment at the point A. Now, what is the bending moment at the point A? You don't want to deal with this AY. So simply take moments about A equal to 0. So you get minus MA because it is clockwise, minus, you have to integrate this load. So what is, so you need to integrate Q of X from 2L/3 to L/3. And what is the lever arm? It is x dx. So as I already said, this is so this is nothing but the centroid of this triangle multiplied by the area of the triangle. So this is equal to minus MA minus the Q of x is linear. So this is a triangle. So this means the area of triangle, under the lobe, right? Multiplied by centroidal distance. This is equal to 0. So what is the area of the triangle? It is half into height of the triangle into base of the triangle, which is L/3. This one multiplied by centroidal distance. So for this triangle, if you have a triangle like this, you can note this down. The centroid of the triangle, if it has a base of length b and a height of length h, the centroid of this right triangle is at a distance b/3 from the longer edge. So from this vertex, it is 2b/3, and from this edge, it is b/3. Similarly, this is h/3. This is 2h/3. So this is where the centroid lies. So the centroidal distance in this case is L/9 from this point. But this is already 2L/3. So it is 2L/3 plus why L/9? It is 1/3 of L/3. This is the 2L/3 plus L/9. So this is nothing but 6L/9. So you will get it as MA is equal to, take it to the other side, you get minus 6L/9, 7. And 3 9s are 27, 54. You will get minus 7 WL² by 54. So minus sign means the assumed direction is wrong. So you have a counterclockwise moment of minus 7 WL² by 54, which is how do. So let's move on to the next question. So let's draw the shear force diagram of this beam. So what is shear force? It is one kind of the internal forces. If you idealize this beam as have an internal hinge and you have a cantilevered fixed support. So this is A, B, D, and C. So you have a continuously distributed loading of 10 kilonewtons per meter. And each of the span is 2 meters. This is 2, 2, and 2. Now, as usual, the first step is isolate. So replace this with the vertical force. Again, horizontal forces are 0 because it's a beam. You have AY. There's no moment. It is a hinged support. Here you have By and Bx is 0 because it's a beam. So if you consider the next span, here there is no concentrated force that is acting. So the shear force has to be continuous. So this will have a downward force of By. And here you will have, if you isolate here, you'll have Cy. Tx will be there, but it is continuous. So this point on the beam corresponds to a continuous, as I drew already. The point C is just continuous. So you'll have, if you have moment MC this side, it will be the same this side. It is not discontinuous. And if you have a shear force Cy this side, you'll have equal and opposite shear force this side. So you will have MC. And on this side, you will have MC, equal and opposite MC. You'll have dy, md. This is the assumed convention. of course, you have the distributed loading. So call this W. Now let us write down the draw the shear force diagram. So what is the shear force? So the convention that I am using for shear forces, this is a beam. We take a section here, we get two parts. Shear force downwards on the left side is positive, and shear force upwards on the right segment is negative. So if the shear force tends to rotate the beam segment clockwise, it is positive. So this is what is followed in Hibbler, RC Hibbler. And following the same thing. One of the textbooks mentioned for this particular course. So with respect to this sign convention, the shear force is so AY is if a positive AY means IAY acts upwards. So in this case, we don't know BY, but this is a simply supported beam. This particular segment, since it doesn't have any moment, this acts as a simply supported beam. So for the section AB, for the segment AB, you have positive AY, which is equal to WL by 2. The total force is WL. Left and right will have equal and opposite. So AY is equal to BY is equal to WL by 2. Simple. But note that BY acts in a direction opposite to our assumed sign convention. On the right side, if the shear force is acting downwards, it is positive, but it's acting upwards. So it is. This is what you will get for the segment AB. So this will be so WL by 2, which is 10 into 2 by 2, 10. 10 kilonewtons. So this is the segment AB. Now look at the next segment, BC. So here you have a moment MC. We don't know how much the moment is. How do we determine it? Again, use the equations of equilibrium. So if you enforce sigma Fy equal to 0, you will get By minus By plus Cy minus WL equal to 0. You will get Cy as, we found By as already WL by 2. You get Cy as 3WL by 2. So which is nothing but 30 kilonewtons. Again, Cy is acting, so it is 30 kilonewtons upwards. So since Cy is acting upwards, but our sign convention is positive downwards, you get this. This is the shear force. Left side it is minus 10 kilonewtons. Here it is minus 30 kilonewtons. Now coming to this point, the last segment, which is CD. See, this is BC. So the shear force at the point C is 30 kilonewtons downwards. So here we're getting it downwards, but on the left face upward is positive. So here it is 30 kilonewtons. And at D, what do you get? dy. Sorry, here Cy is missing. Cy. You get dy is equal to Cy from sigma Fy equal to 0. So what does that mean? So dy is also equal to minus 30 kilonewtons. This is a flat segment at minus 30 kilonewtons. So finally, our shear force diagram is something like this. This is how it looks. So this is the point A, this is the point B, this is the point C, this is the point D. So this is 10 kilonewtons, minus 10 kilonewtons, minus 30 kilonewtons, and it goes. So this is the answer. So going to the next question. Now here we need to find the maximum bending moment. So here is the trick. So as I said, we adopt the principle of superposition. Principle of superposition. So you have two types of load. One is this one, which is a distributed load, and the other is 30 kilonewtons, which is a concentrated force. And the other one is this concentrated moment. So The structure we have is this. This is the base structure. This is the base beam which you have. And you have three types of loads, and those three types of loads can be decomposed as this plus. This plus. You take one load at a time, find the response of each of them, plus, and add them all up. This is 30. Okay. So now it is simple. So what is the bending moment diagram? In this case, if you take a section anywhere in between, it doesn't have any force. So there is no shear force in this, because since there is no force acting at this span, wherever you take a section in this, if you expose the internal forces.
Yes, I just need to do this one. Okay. And this is the signature.
You don't have any force acting in this, so it is just the moment. You just enforce sigma Fy equal to 0 at any point, at any internal point in this beam, you get is Fy equal to 0, which means V equal to 0.
You can put it on the bed or then apply bandage or anything so that it will just stick on the patient.
And if you enforce sigma M equal to 0, you get Mx equal to 5 kilo. So
this is the medicine that they are not just think center.
at this point, you have a vertical force. And how much is that? You can enforce the equations of equilibrium as usual.
This one also you have to see. This one is good. This is covered this, this one, and this one is so. Conditions. Okay, you have to take one of this. This will be okay. You give this one to you. Right.
So what do you get? You get
Thank you.
so what it is? -5. -5, -120. Plus Cy to 8 equal to 0. You get Cy as 125 by 8. Just a minute. Let me take another page. Let us consider the first case. Where you just have this concentrated moment. So in that case, you get take moments about this point. This is 5, this is 8. So is this the point? I guess C is this is B, this is A, this is C. So Cy into 8 minus 5 is equal to 0, which means Cy is equal to 5 by 8 kilonewtons. But By is equal to minus C1 because they are the only two forces acting on this band, which means By is equal to 5 by 8 kilonewtons downwards. Yeah. Yeah, so up By is upwards and Cy is downwards. So it means at this point you have, so at this point, if you draw the bending moment diagram, you get minus 5. And the point C is a fixed point, so hinged point, so it has to have 0. So this is the first part. Coming to the second part, you have a concentrated mid-span load of 30 kilonewtons. And this is it is kind of simply supported. These portions are free of any shear force or bending moment. And this 30 kilonewton causes a moment that is proportional to this distance. So if you recollect your basics, this will have the bending moment diagram of PL by 4. In this case, so from the first part, you get this minus 5 kilonewton meters. And in the second case, you get this 30 into 8 by 4. So that is 60 plus 60 kilonewton meter. So it should be upwards plus 60 kilonewton meters. And in the last case, you have a uniformly distributed load. So this is equivalent to you have one span which resists a moment of MB. You have one span which resists the moment MB and a certain reaction. So reaction should be equal to the total force, which is 10 into the span is 5. So a total reaction of this much. And MB should be equal to the total moment it has to resist. So that will be equal to minus 10 into 5 into where does it act? So 2 point, which is minus 125 kilonewton meter. And how does it vary? So the loading, which is dV by dx, is quadratic, is constant, which means V is linear and M is quadratic. So, and again, the force should be 0 right here. So the loading that you get in this case will be, it increases quadratically up to a point of 125, like this, and then it goes back to 0. So superpose this one, and this one. You get at this point minus 5 plus 60 minus 125 kilonewtons meter. So sorry, it's not 60. At this point, it is 0. So in this case, it is 0. So the maximum moment is minus 130 kilonewtons meter. So the final moment diagram will look something like this. This is what it looks like. Here, this is. Now the next one is a simpler question. So we're almost time. So let us look at this. So again, first step, idealize. Have a linearly distributed load on both sides. Now what is required? We need to determine the moment and the vertical reaction at A. And we have an internal hinge at B. So we have idealized it. So consider the second span alone, BC, of 2 meters, 8 kilonewton. Let us determine the support reactions. So you have BY, CY, and a linearly distributed load. Now take moments above the point C. We don't need CY, we only want BY because it is the same thing that is applied here. So this is BY, AY, ME. And we have this linearly distributed load. So to determine BY, take moments about the point C, MC. Moments about the point C. So what do we get? 8. It's a triangle. So as I said earlier, BY into 2, it acts clockwise. So minus and plus 8 into half into 2. And where does it act? The centroid of a triangle is 1/3 from this side, 1/3 of this piece into 2/3 from this side. So is equal to 0. So what is BY? You get BY as so you get BY as 8/3 kilonewtons. You can check this. So 2 cancelled, 2 cancel, we'll get 8/3 kilonewtons. And to this span, you need to find the vertical moment and the vertical reaction and the move. So what you have here is a cantilever beam with a tip force of 8/3 kilonewtons and a linearly varying force of maximum intensity 12 kilonewtons per meter. So again, to determine the total force, what is it? AY is equal to AY minus 8/3 kilonewtons minus half into 12 into 3 kilonewtons is equal to 0. So AY is equal to 8/3 plus 18, which is nothing but 20.67 kilonewtons. And just take moments about the point. So we will get minus 8/3 into 3 minus half into 12 into 3 into, where does it add? 1/3. So it is into 3/3. Which is nothing but 18 and this is 8. So it is minus 20 kilonewton meter. The moment at the point, moment about the point A. So that's all. So the moment at the point A is 20 kilonewtons meter. Sorry, just in it. This is 8, right? Yeah, so not 8, 20, 26 kilonewtons meter, and the reaction, vertical reaction is 20.67. Then yeah, so here we are asked to find out the vertical reaction at the intermediate support. So as usual, let me skip some steps. So at the intermediate support, vertical reaction at the supports D and F. So let us start from the right side. So if you take the right side, you have E is an internal hinge, F is a roller support. So what E cannot resist the moment, so it can be treated as what you have is a vertical force EY, and you have 16 kilonewtons. And this is F. So this acts as a simply supported beam. So this is equal 4 meters and 4 meters. So you get EY as 8 and Fy as 8 kilonewtons. Now go to the next span. We have this is E, this is E, this is C, which is also an internal hinge. And here you have a support D. So this becomes, you have a force dy, and this is 4 meters, it's 2 meters. You don't have any loading on it, but you know that EY is 8 kilonewtons. So here you have 8 kilonewtons, and here you have an unknown force CY. Here you have an unknown force CY. So I say it acts upwards. And if you consider the remaining portion of the beam, you get you have CY acting downwards, equal and opposite. This is 4 kilonewtons per meter. Here you have this 8. So what is the total force that is coming onto this span? It is, you want to determine CY. So take moments about just a minute. So C, D, there is no loading on this span. Yes, so consider this system. So if you take moments about the point C here, what do you get? You get dy into 4 minus 8 into 6 equal to 0. So you get dy as 8 into 6 by 4. So that is nothing but 12. So that's all. So dy is 12 kilonewtons and Fy is 8 kilonewtons. So that's all the problem. You want to find out the other reactions Cy, Ay, and others, you can go on with this process. Once you have determined dy, you can find Cy. Why? Cy plus dy minus 8 equal to 0. So you will get Cy as minus 4 and so on. You can keep going, you can keep taking it forward and determine all the reactions and the internal moments. We don't have much time, so I'm skipping those steps. Now, yeah. Now determine the maximum shear force and the bending moment in this problem. So the procedure is as follows. You can take same thing. So first step is to isolate. So you have, let us call it AB. So this is the point A. Determine the reactions as usual. So where does the equivalent load act? It acts at 2L by 3 plus L by 9. We have already determined it. So that is at 7L by 9. How much acts? W L by 6. So by simple mathematics, you can determine that AY is equal to 2 by 9 of WL by 6. And By is equal to 7 by 9 of WL by 6. So how does this come? Enforce moments about A equal to 0 and moments about B equal to 0. You'll get this directly. Once you have determined this, split the beam into two parts. One is this part where you have AY acting at where you have AY and this. Call this point C. There are certain unknown forces here, but you need not worry about them. What we want is the maximum bending and moment and shear force. And consider this portion CB. So if you cut at the distance X, you get a constant shear force diagram in this switch. So what is it equal to? It is equal to this value. And left up is positive. So this is positive shear force of 2WL by 54. And on the right hand side, you have a linearly varying force. So how much is By? It is 7 by 9 WL by 6. 7 by 9 WL by 6. And this side, it is continuous at this point. There is no discontinuity. So you get. And this is a negative shear force. So here you have a minus. This is 2L by 54. And this is 7 WL by 54. This is negative, this is positive. So wherever this crosses this line, take that point and take moments of these forces above this point. So wherever this crosses it, right, this will divide the line in the same fraction. 2 by 54 and 7 by 2 plus 7 is 9. 2 by 9 to 7 by 9. So this divides the line in the same fraction. So find the moment at this point, that will be the max, because if M is maximum, dm by dx is equal to V is equal to 0. So by this, you get maximum bending moment at this point, and the maximum shear force by magnitude will be here. The yeah. So compared to 7 WL by 54 and 2 WL by 54, you see this is maximum. So that is it. So getting to the last problem of the day. This is easier. We are not finding any bending moments. So this is a two-way slab. This is what we have. To determine the loading that comes onto the beams that support the slab, there's something called this yield line method, where you divide the slab by 45-degree lengths and take the line load acting directly on this. This is if you consider the beam AB, you have a trapezoidal loading. Of maximum intensity. So this is 5. So this is 5. 5. So 5 into thickness into raw concrete into G. So that is the load that comes onto this. 5 is the width, and this is linearly varying. So given this, you know what is the support reaction. So this is the area under this triangle plus the area under this rectangle up to half length. So the force that you get in the total force that comes onto this will be 70.5 kilometers. And if you take this portion of the slab, this will be 5 into T into rho C into G. This is the intensity. Now the area, so the force that comes down to BC, half of this. So it is half into 5 into 5 into G into rho C. So that comes to 35 kilometers. So in this, so this beam transmits 70.5 kilometers. This beam transmits 35 kilometers. So total column force 105 kilometers. So you can check this. This is a simple problem. You just have to consider, divide it, find the area under this, divide it by half, and take it to each of these steps. Same way, find the area under this, divide it by half, take it to each of these steps. Divide it by half, and divide this by half, take it to each of these steps. So consider, so each of this will receive a load of half from this and half from this. So this is the last problem for the day. Thank you. Let me stop sharing the screen. I hope you learned a lot from this session. Are there any doubts that I can clarify? As I said, the recording will be made available on YouTube. You can review it as and when you like it. If you haven't followed any section, you please let me know in the next session. I will go through those problems again. I can resolve the doubts. I was a bit fast towards the end as I was running short of time. So in case you have any doubts in those particular problems, I will do it by the next session. So are there any doubts that I can clarify before ending this? Could anyone unmute and let me know if there are any doubts? Or if you want more time, you can go through it and come back. Okay, it seems like there are no more doubts. So thank you. We'll meet next week at the same time. Thank you for your attendance. Thank you. So I'm stopping the recording here.